Dear students, in this class we will learn about nanochemistry, that is unit 2 of your paper. So in the syllabus you have to learn about the terminology, scales of nanosystems, nanoparticles, nanomaterials, that is its synthesis, all these techniques, that is a chemical precipitation method, mechanochemical method, microemulsion method, reduction technique, chemical vapor deposition, and sol gel method. So only a brief study is required. Then you have to learn about the properties and applications of fullerenes and carbon nanotubes. Then you also have to learn about nanochemical devices, optoelectronic devices, photo detectors, that is LED, and lasers. So first of all, you have to get an idea about the size of nanomaterials, that is the size range of nanomaterials. For that, you can see this picture. So in this picture there is a scale shown here. So here from 1 nanometer to 100 nanometer, any material whose dimension come between this range, between 1 nanometer to 100 nanometer, these are called as nanomaterials. So we know that any material can have 3 dimensions, isn't it? X, Y, and Z axis. All these 3 dimensions are possible. So if any one of these dimensions lies in this range, that is between 1 nanometer to 100 nanometer, we can say that it is a nanomaterial. Okay, so this picture also shows all the other common materials which we come across. For example, a volleyball, you know the size range. Okay, so here again we know the size of red blood cells. It is typically coming around 10 micrometer. Again, if we reduce the size, we will reach nanomaterials, and then again if we reduce the size range, we will reach the DNA, which is a biological hereditary genetic material. And again, if you are reducing the size, we will reach atom, that is around Armstrong unit, 1 Armstrong unit. Okay, so these are the a typical idea about the size range. So nanomaterials means a material whose any one dimension will come under this range, that is between 1 nanometer to 100 nanometer. So nanomaterials are materials having at least one of their dimensions, length or width or height, in the range of 1 to 100 nanometer, and this range is called the nanoscale or nanoscopic or nanometric range. Now the word nano, it is a unit prefix that originated from the Greek word that means dwarf. Okay, and 1 nanometer means it is 10 raised to minus 9 meter. This is very important. 1 nanometer is equal to 10 raised to minus 9 meter, or it is nearly 10 Armstrong. So in your text you have a very good introduction in this unit. You have to read through that. So in recent years, nanotechnology has become one of the most important and exciting forefront fields in physics, chemistry, engineering, and biology, and it shows great promise for providing us in the near future with many breakthroughs that will change the direction of technological advances in a wide range of applications. And nanotechnology is the design, characterization, production, and application of structures, devices, and systems by controlling shape and scale. So here you can get an important question. What is the difference between nanotechnology and nanoscience? Okay, so here you have a small definition here. Nanotechnology means it is a design, characterization, production, and application of structures and devices and systems by controlling shape and scale. Okay, so it means it is the design of nanomaterials. Okay, and how these nanomaterials designed for a specific purpose can be applied in devices and systems. Okay, so this is a nanotechnology, what it implies. Okay, so the transition from microparticles to nanoparticles can lead to a number of changes in physical properties. So when we consider bulk material means any particle whose size is greater than micro or in the range of micro. Okay, when we consider this bulk particle, it may be having certain properties. Okay, certain physical properties. But when we are reducing the size of these bulk particles, so many peculiarities can be introduced in these materials. That is, when these bulk or microparticles reach the nano dimensions. Okay, two important factors are there. That is, first one is that in these nanomaterials there is an increase in the ratio of surface area to volume. Okay, ratio of surface area to volume. So when the material is reduced to a nano dimension, more number of atoms are present on the surface rather than on the inside the bulk of the material. So as a result, the surface energy of these particles will highly increase, and because of that certain properties like improved catalytic activity, all such properties will be introduced in this nanoparticle. So the reason for this is the increased ratio of surface area to volume. Okay, and second factor is that quantum confinement effect will predominate in these particles. That is, confinement means it is actually certain charge carriers. That is, inside these systems we know that the electrons and holes are the charge carriers in these systems. So when these materials are reduced in their size, these charge carriers are confined to a particular region. Okay, that is, between this 1 to 100 nanometer, these charge carriers will be confined. That is, it will not be allowed to move outside this region because of this size limitation, or because of the changes happening in the energy band gap of these materials. So this is the quantum confinement effect. So two important effects occur when the microparticles are converted to nanoparticles, when the size of any material is reduced to nano dimension. First is the increase in the ratio of surface area to volume. Okay, and second is the quantum confinement effect. That is the confinement of charge carriers within the nanomaterials. So the increase in the surface area to volume ratio, which is a gradual progression as the particle gets smaller, leads to an increasing dominance of the behavior of atoms on the surface of the particle over that of those in the interior of the particles. So when the surface area to volume ratio is increasing, it means that the number of particles on the surface of the material will be more than that inside the material. Okay, if you are taking a bulk material, a bulk particle, a particle with very larger size, we know that there will be more number of atoms inside the bulk of that material and lesser number on the number of atoms on the surface. But in reverse to that, in the case of nanomaterials, more number of atoms will be on the surface and lesser number of atoms will be in the bulk of the nanomaterial. Okay, so this affects both the properties of the particle in isolation and its interaction with other material. So we know that if the number of free atoms on the surface is greater, the surface energy of that particle, of that nanoparticle, will be very higher. So this will affect many of its properties, including its interaction with other materials. Other materials means it may be either a bulk material, it may be a polymer material, or it may be the same nanoparticle itself. Okay, any material which we mix the nanoparticle with. Okay, so both the interaction as well as the properties inherent in the nanomaterial will be influenced when this surface to volume ratio is changed. So the nanomaterials, next paragraph, nanomaterials are structures at the nanometer scale, that is 1 nanometer is equal to 10 raised to minus 9 meter. It is comparable to that of atoms and molecules. The nanomaterials are developed to exhibit novel characteristics compared to the same material without nanoscale features such as increased strength, chemical reactivity, conductivity, etc. So when a material is reduced to its nano dimension, reduced to a nano size, what happens? Certain novel characteristics are introduced inside these nanomaterials. Okay, newly developed novel characteristics are introduced inside this nanomaterials. For example, the newly formed nanomaterial might be having increased strength, toughness, tensile strength, etc., or it may be having high chemical reactivity, or its electrical or thermal conductivity can change. So all these are novel characteristics which may require for technological applications. Then nanoparticles can comprise a range of different morphologies, including nanotubes, nanowires, nanofibers, nanodots, etc. This sentence, it actually is talking about the shape or the morphology of the nanoparticle. Okay, morphology means we know the physical structure, how it looks. It may be either looking like a tube, and then we'll call it as a nanotube, or it may be a thin wire in the nano dimension, so we'll call it as nanowires, or it may be fibers, or it may be a dot. Dot means it is talking about the quantum dots. Okay, semiconductor quantum dots, so we call it as nano dots. Okay, and even other materials which are not semiconductors can also be synthesized in dot forms. Okay, they are also called as nanodots. So the morphology can vary. Okay, and these materials have seen applications in a wide range of industries, including electronics, pharmaceuticals, polishing, catalysis, and in the next few years we will see a dramatic increase in their industrial generation and use nanoparticles. In the next page we are talking about the classification of nanomaterials based on its dimensionality. Okay, so nanomaterials, it can be classified based on different criteria. Okay, if it is based on the electrical properties, they can be classified as conducting, superconducting, or non-conducting nanomaterials. Okay, conducting means it might be synthesized from any metals. Okay, metallic nanoparticles will be there. Then if it is a superconductive, means it might be of a semiconductor nanomaterial. Then you also have non-conducting or an insulator nanoparticle. And based on magnetic properties, it may be either magnetic or non-magnetic nanomaterial. So you might have heard about super paramagnetic iron oxide and all. Okay, all these are nanoparticles of the dimension 1 to 10 nanometer. 1 to 10 nanometer. So because of its highly very miniaturized dimension, these nanomaterials are able to express super paramagnetism. And then another method another classification, it is based on their dimensions. We have earlier mentioned, there are 3 dimensions. Okay, 3 dimensions in either in the x, y or z axis. So on the basis of dimensions, these 4 classifications are there. That is 0 dimensional nanomaterials, 1 dimensional nanomaterials, 2 dimensional nanomaterials and 3 dimensional nanomaterials. Let us see what is the 0 dimensional nanomaterial. So in a 0 dimensional nanomaterial, you can see a picture here. Okay, a 0 dimensional nanomaterial, it might be a quantum dot, or it can be a fullerene, or a gold nanoparticle. Okay, AU, it stands for gold. So all these are dots, or these are nanospheres. So nanospheres means it is simply composed of a cluster, a group of few atoms. Okay, and it will lie in very small range, within this nano range. So these are called 0 dimensional nanomaterials. And now we can see 1 dimensional nanomaterials, that is nanotubes, wires, rods, etc. All these particles in this shape, okay, in tube shape, all these are comes under the category of 1 dimensional nanomaterial. Examples are ceramic crystals, metal nano rods, then carbon nanotubes and gold nanowires. Even this gold nanoparticle, it can be synthesized in nanowire form. Okay, so these are all examples for 1 dimensional nanomaterial. And the third category is 2 dimensional nanomaterial, which is thin films, plates, layered structures, etc. All these structures, you can see a most common example here, that is graphene sheets. Okay, graphene is composed entirely of carbon atoms, isn't it? So here this allotropic form of carbon, it can be changed into a sheet like structure like this, and it can also be converted into layered nanomaterials. Then you have carbon coated nanoplates. Okay, so in carbon coated nanoplates, over any a plate made of any material, we simply coat carbon atoms using suitable synthesis techniques. And also the third category is 3 dimensional material, that is bulk nanomaterial or polycrystals. So polycrystalline materials, dendrimers, then liposomes, all these are 3 dimensional or bulk nanomaterials. So these are the 4 important classification of nanomaterials based on dimensionality. So what do you mean by all these classifications? How are we able to classify this? So let us see the 0 dimensional nanomaterial. So in 0 dimensional nanomaterial, all 3 length scales, that is length along x-axis Lx, length along y-axis, that is Ly, and the length along z-axis. So all 3 length scales are in the nanoscopic range. You know this nanoscopic range, isn't it? That is 1 to 100 nanometer. So all these 3 length scales of this material will lie in the nanoscopic range. So example is quantum dot, metallic, nanoclusters, nanospheres, nanorods, nanocubes, etc. So all these are examples of 0 dimensional nanomaterials. Now in 1 dimensional nanomaterial, here one of the dimensions is out of the nanoscopic range. Okay, that is the other 2 dimension. Among the 3, the other 2 dimension will be inside the nanoscopic range, while the third dimension will be out of the nanoscopic range. That is, it will be above 100 nanometer. In this case, in the case of a 1 dimensional nanomaterial, you can see the structure of a nanotube here, isn't it? So this is a 1 dimensional nanomaterial. Here the length scale is out of 1 dimension, that is, it is greater than 100 nanometer, but the other 2 dimension will be within this 100 nanometer. So here when we talk about the confinement effect, the charge carriers along these nanotubes, it is free to move along this one dimension. Okay, so the charge carriers means the electrons or holes, the electron hole pairs are free to move along this length, along this dimension. Therefore it is called one dimensional nanomaterial, while the charge carriers are confined in the other two dimension. Okay, and again in the two dimensional nanomaterials, any two dimensions are out of the nanoscopic range. That is, among the x, y and z axis, the any two axes, so the any two dimensions are out of the nanoscopic range. That it is greater than the greater than 100 nanometer, while one dimension, any of the one dimension will lie within the nano range. For example, you can see thin films. Okay, thin films are two-dimensional nanomaterials. It means that in these you can see that for example, along the x and the y axis, the size of this material is greater than 100 nanometer, whereas along the z axis, that is, we typically talk about the thickness of this one layer. Along this z axis, the material will be confined to the nano dimension. That is, the charge carriers will be confined along this third dimension. I hope you understand. So this is typically the characteristics of a two-dimensional nanomaterial. So in a two-dimensional nanomaterial, any of the two dimension will be greater than 100 nanometer, while the third dimension will be lying within the nano range. Okay, that is it will be between 1 and 100 nanometer. Therefore the charge carriers will be confined only within this 1 and 100 nanometer size of this material. Okay, and these are the typical examples: nanofilms, nanosheets, and nano coatings. All these are considered as two-dimensional nanomaterials. Now let us see this third-dimensional, three-dimensional nanomaterials. In these materials, all three dimensions are out of the nanoscopic range. So there is no confinement at all. Okay, confinement of charge carriers along any of these dimensions, because all the three dimensions are out of the nanoscopic range, that is greater than 100 nanometer. Therefore we say that it is a bulk nanomaterial. Now let us come to your text. Here the classification based on nanoscale dimensionality is given. So based on the number of dimensions which lie within the nanoscale, nanomaterials can be classified into three categories. First is nanosystems confined in one dimension. Okay, so confined in one dimension means so in these materials that have one dimension in the nanoscale, but they are extended in the other two dimensions. Okay, and thin films or nano layers or nano coatings, all these are surface coatings with thickness in the nanoscale. All these are examples of nano systems confined in one dimension. And here nano system confined in one dimension means the materials that have one dimension in nanoscale range but are extended in the other two dimension, which is typically a two-dimensional nanomaterial. You have to understand clearly the difference. Here the material is extended in other two dimensions. Okay, and in the second classification it is written that nanosystems confined in two dimension. So here in this case two dimensions are confined in the nanoscale, but they are extended along one direction. So typical examples are nano wires, carbon nanotubes, etc. So this is actually example for one-dimensional nanoparticles. And in third classification it is mentioned that nanosystems confined in three dimensions. So all the three dimensions are confined. You know that quantum dots or nano dots are typically confined in all the three dimensions, that is along x, y and z axis. So these are actually zero dimensional nanoparticles, quantum dots or nano powders made of gold nano or silver nano. All these are examples of zero dimensional nanoparticles. Now, why is nanotechnology important? Many benefits of nanotechnology depend on the fact that it is possible to tailor the structures of materials at extremely small scales to achieve specific properties. Tailor means to alter. So it is possible to alter or modify the structure of materials or bulk materials to extremely nano scale, so that we can achieve or we can incorporate certain specific properties which we need. For example, if you want to increase the conductivity or if you want to increase the toughness of certain materials, it is possible. Okay, so certain specific properties can be incorporated by manipulating or by tailoring the structure of materials. Then using nanotechnology, materials can effectively be made stronger, lighter, more durable, more reactive, more sieve-like, or with better electrical conductivity, then among many other traits. So many everyday commercial products are currently on the market and in daily use that rely on nanoscale materials and processes. So all these are the typical fields of research in which innovative applications of nanomaterials are daily research. For example, in the field of energy. Okay, in the field of energy, numerous nanomaterials, for example carbon based electrodes or polymer nanocomposites incorporated with nanomaterials, all these are actively researched. For another example is in the area of medicine and drugs. For example, dendrimer nanoparticles, all these are used for drug delivery applications and all. Then nanotechnology as a whole, then in nano devices, then optical enhancers or something, I can read that. Then defense and security. In the field of defense and security also, many type of nanomaterials are being used, and it has been actively researched by our country also. Okay, then in the field of bioengineering, in commerce, in nano fabrics, so all these are numerous innovative applications of nanotechnology. Then let us see this paragraphs. So here the applications are given in detail. The nanoscale additives to or surface treatments of fabrics can provide lightweight ballistic energy deflection in personal body armor, or can help them resist wrinkling, staining and bacterial growth. So nanoscale additives means certain nanomaterials or nanoparticles. These are used or coated over fabrics. Okay, through surface treatments. Certain chemical procedures are used, and these nanomaterials are coated over fabrics. So as a result of this, these fabrics can be converted to lightweight ballistic energy deflection in personal body armor for security purposes and all. This type of fabrics can be used so that it can prevent this ballistic penetration of small bullets and all. Okay, and also this type of fabrics, it will not wrinkle or it will not be stained easily. And certain type of fabrics can also have antibacterial property depending on the type of nanoparticle coat. For example, silver nanoparticle is having antibacterial property. So if silver nanomaterials are coated over these fabrics, then this bacterial growth can be prevented over this fabric. Then clear nanoscale films on eyeglasses, computer and camera displays, windows and other surfaces can make them water and residue repellent, anti-reflective, self-cleaning, resistant to ultraviolet or infrared light, then anti-fog, antimicrobial, scratch resistant, or electrically connected. So all these are applications of nanomaterials in which of nanoscale films. Okay, so films means over a type of typical glass material, nano materials are coated, or a typical two-dimensional nanomaterial is made out of these materials. Okay, then in bioengineering of enzymes is aiming to enable conversion of cellulose from wood chips, corn stalk, unfertilized perennials, grasses, etc. into ethanol or fuel. So we are able to extract this ethanol or for fuel purpose. So biofuels can be made from these materials. Okay, biomaterials like wood chips, corn stalks, all these things. So for that, certain enzymes, bioengineered enzymes can be applied for this purpose. Then cellulosic materials have demonstrated potential applications in a wide array of industrial sectors, including electronics, construction, packaging, food, energy, healthcare, automotive, and defense. Then cellulosic nanomaterials are projected to be less expensive than many other nanomaterials, and among other characteristics toward an impressive strength to weight ratio. So here in all these cases we are able to synthesize cellulosic nanomaterials which are actually less expensive and which also have high strength to weight ratio. So all these are the advantages of nanotechnology. Then next paragraph, nano engineered materials in automotive products include high power rechargeable battery systems, then thermoelectric materials for temperature control, tires with lower rolling resistance, high efficiency or low cost sensors and electronics, then thin film smart solar panels and fuel additives for cleaner exhaust and extended range. So all these are applications of nano engineered materials either in the automotive industry or in the energy industry. Okay, energy industry means for the manufacture of high performance rechargeable battery systems. Then you have this nanostructured ceramic coatings. It exhibit much greater toughness than conventional wear resistant coatings for machine parts. The nanotechnology enabled lubricants and engine oils also significantly reduce wear and tear, then which have significantly extend the lifetimes of moving parts in everything from power tools to industrial machinery. So you know that this nanotechnology enabled lubricants and engine oil means for example we can use nanofluids. Nanofluids are typically liquid materials in which nanoparticles are dispersed. So these nanofluids can be either used as a lubricant in these machine parts, or it can be used as coolants. So all these are there are numerous applications of nanotechnology in various fields like this. Then nano engineered materials make superior household products such as degreasers and stain removers, then environmental sensors, then air purifiers and filters, antibacterial cleansers, and specialized paints and sealing products such as self-cleaning house paints that resist dirt and marks. So all these are some other applications of these nano materials. The nanoscale materials are also being incorporated into a variety of personal care products to improve performance. The nanoscale titanium dioxide and zinc oxide have been used for years in sunscreen to provide protection from the sun while appearing invisible on the skin. So here these are a list of applications of nanomaterials or nanotechnology, okay, in various fields. And in the next section you are dealing with synthesis of nanomaterials. So basically nanomaterial synthesis can be of two approaches. First is the top down approach and second is the bottom up approach. A top down approach means size reduction from bulk materials, and bottom up approach means material synthesis from atomic level.